Today?
Totally awesome, sir.
Wonderful. So we're working on lesson 2, projectile motion unit. And the question is, how can horizontally shot projectile motion problems be solved? How can horizontally shot projectile motion problems be solved?
You do 2 problems. It's a great question. It's cool.
Basically, like if you're up on a cliff and you throw a stone horizontally, the stone is going to follow that parabolic trajectory. And we're going to solve things like how far from the base of the cliff does the projectile go? How much time does it take while it's in the air? What's the final velocity right before it hits the ground? Things like that. The bottom line is the answer to this question is rather simple. What we're going to do is consider the horizontal motion and the vertical motion separately, even though both of these motions are happening at the same time. But we discussed in lesson number 1 how the horizontal motion is uniform motion, and the vertical motion is uniformly accelerated motion. So let's look at a sample problem. Let's say there's a cliff and a student stands on top of the cliff and throws a rock horizontally. And of course, in later lessons, we're going to work out how to solve the problems when the projectile is thrown at an angle. But for now, we're starting off with horizontally thrown projectiles. And let's say we want to figure out how far away from the base of the cliff does the rock land. This is referred to as the horizontal displacement, and since it's a displacement, you can give it a symbol x. But since it's the horizontal displacement, sometimes a helpful subscript is used, sub x. It's the displacement in the x direction, x sub x, whereas the height of the cliff over here, that's the displacement in the y direction. So over here we could say x in the y direction, x sub y equals 15. Yes.
X sub x is called the range.
And x sub x is called the range. Just like when you go to a golf range, you see how far away the ball lands. Not like the range in math class, which is the vertical values. So when you go to solve this problem, basically what you want to do is analyze the horizontal motion, knowing that here it's going 10 meters per second horizontally. Here it's still going to be going horizontally 10 meters per second. Here it's still going to be going horizontally 10 meters per second. And even right here, right before it hits the ground, it's going to be going horizontally 10 meters per second. The horizontal motion is constant. But while that's happening, we have a vertical motion. Now at first, vertically speaking, it's not going up or down at all. It's only going horizontally. Then a moment later, it's going a little bit vertically because gravity has started to pull it down and it's accelerating downward. A little while later, it's going even faster vertically. And a little while later, it's going even faster vertically. I'm not sure what these values would be, so I'm not going to put numbers down there. But if they were at 1 second intervals, I'll tell you this, which they're not because that cliff is not high enough. But if they were, then this first one would be 10 meters per second, this one would be 20 meters per second, and this one would be 30 meters per second. Because it would be accelerating at the acceleration due to gravity. So with this as our backdrop, we go to do the solution. And what you should do is make a big chart where you break half the page up, one for the horizontal motion, and the other half of the page for the vertical motion. Some people just label X for horizontal and Y for vertical. I suggest you make a big T chart, so it looks like a T. And then every calculation and every piece of data is either going to go in the horizontal column or the vertical column. And you start to really break it down into two motions occurring simultaneously yet independently. And the first thing you want to write down is the acceleration in each direction. The acceleration in the horizontal direction and the acceleration in the vertical direction. Now, since it's going with a constant velocity, horizontally speaking, what's going to be the acceleration in the horizontal direction, John?
0.
0. Meanwhile, while that's happening, vertically speaking, the projectile is going to be going faster and faster and faster, so it is accelerating. So what's the acceleration in the vertical direction going to be? Tim?
Negative 10 meters per second.
Negative 10 meters per second squared. And it's negative 10, not because it's slowing down, but because it's going down. And it's very common to choose, down as the negative direction. Now, you don't have to choose down as your negative direction. If you wanted to, you could say, hey, I'm going to let down be the positive direction. And then over here, this would be positive 10. Because it would be going faster and faster and faster in the positive direction. I'm going to stick with the, the negative orientation. With down being negative, because that's more in line with what we're going to be using in the future. So might as well start practicing that way. The next thing you might want to list is the velocity in each direction. How fast is the projectile initially going horizontally, and how fast is the projectile initially going vertically? Now, if we look back at the original problem, they tell us the projectile was thrown horizontally at 10 meters per second. That's how fast it's going horizontally. So if we go over to our solution here, the horizontal initial velocity is 10 meters per second. Meanwhile, though, right at that first instant, the first instant it's thrown, how fast is the projectile going vertically? Retain?
It's at rest.
Yeah, it's at rest. 0 meters per second. Because at that first instant, it's not going up or down. It's tricky business, though, because the very next instant, it's already started to go down. But the very first instant, 0 meters per second. Now, you can leave the data just like this. Some people find it useful to give the data helpful subscripts to remind them that it's horizontal or vertical. And X is used for horizontal and Y is used for vertical. So if you want to, you could go back and say, hey, the acceleration in the x direction is 0, a sub x, and the acceleration in the y direction is a sub y. Other people find the subscripts confusing, but if they're helpful, you can add them in. The initial velocity in the x direction was 10 meters per second. The initial velocity in the y direction was 0. Now, the other thing we were given is the height of the cliff. So is that going to be a vertical displacement or is that going to be a horizontal displacement? Where am I going to put that 15 meters? My man Jake?
Vertical.
That's vertical. So basically, the displacement x is going to be 15 meters. And since it's in the y direction, vertical direction, some people like to call it x sub y. Some people call it just y. They'll say y equals 15 meters. That's okay too. But if we're using our reference frame where down is negative, if the object started up here and it's going to end up down, then our total displacement is actually going to be negative because it's dropping down. So that's a negative 15. Again, if I chose down to be positive, then both the vertical acceleration and the vertical displacement would be positive. So you can have both of them be positive or both of them be negative. And what we're trying to find is how far away from the base does the ball land. So if we come over here, the displacement in the x direction is our question mark. Now notice the values in the horizontal column are very different than the values in the vertical column. But with a projectile shot horizontally, there's one variable that's going to be the same in both columns.
Time.
Exactly, Kevin, time. However much time that projectile is going horizontally, that's how much time the projectile is going vertically. Time is the one variable that can be swapped over. So usually at this point, you look at your two columns and you ask yourself, which column has more information? Which column is going to allow me to get the time? And then once you have the time, then you usually swap it over to the other column to solve what you need to solve for. So like in this column here, in this problem here, which column do we have more information in the back? William? Pardon? Exactly, the vertical. Okay, we have more information in the vertical, so we could solve for the time in the vertical. And does anyone see what formula that shouts out right there? Yes, Rachel.
A equals VI plus 1/2 AT squared.
Yes. So we have x equals VIT plus 1/2 AT squared. A great displacement formula. And again, if you want, you could put those helpful subscripts. X in the y direction equals the initial velocity in the y direction. Time doesn't get a subscript though, because time is a scalar. It doesn't have direction. 1/2 times the acceleration in the y times time squared. And then you remember, hey, at the beginning, the initial velocity, vertically speaking, was 0. So basically over here, that drops out. And now you substitute in what you have. So you have negative 15 meters is equal to 1/2 times negative 10 meters per second squared times time squared. And then you solve for time. Don't forget to take the square root. And what do you have?
1.7.
1.7 seconds. Since we're not totally done with the problem yet, we want to carry along an extra digit because we have our answers are going to have to be in 2 sig figs. So 1.73 seconds. So now we know the time here is equal to 1.73 seconds. That's how much time it was dropping. But meanwhile, simultaneously, it was also moving horizontally. So we know the time it was moving horizontally was 1.73 seconds. The time is the one thing you could share back and forth. And now that we know how much time it took to go horizontally, how could we solve for that horizontal range? Yes?
The same equation except with the x's.
Yeah, you could use the same exact formula. The great displacement formula. X equals VIT plus 1/2 times acceleration times the time squared. And again, if you want to put the helpful subscripts, x in the x direction equals VIX times the time plus 1/2 times acceleration in the x direction times the time squared. But this time, what are we going to cross out? The acceleration term. This time here, since the acceleration is 0, this whole term here, hasta la vista, so basically you're left with x in the x direction equals VIX, 10 meters per second, times 1.73 seconds. So we know now exactly how far forward that sucker's going to go, and it's going to be 17.3 meters, and if you round it to 2 sig figs, it would be 17 meters. So by considering the horizontal motion and the vertical motion separately, you can solve the problem. So the answer right here is this distance, approximately 17 meters. Now, a follow-up question is, how fast is that rock or ball or whatever it is, how fast is it going right before it hits the ground? And that's referred to as the final velocity. So that final velocity, right before it's going to hit the ground, while it's still a projectile. Well, it's actually going to be going like this, in that direction. You know, right here, its final velocity, right here its velocity is in this direction. Right here its velocity is in that direction. Right here. So another follow-up question is, what is that final velocity? Sometimes students think the final velocity is going to be 0 because once it hits the ground it stops. But that's not the intent of the question ever. It's always the instant before it hits the ground and stops. Now you can't just bam crunch out any one formula to solve for that final velocity. What you're going to have to do first is even break that velocity down into parts. And you're going to have to ask yourself, hey, how fast is that projectile right before it lands? How fast is it going horizontally? And how fast is it going vertically? So you're going to need to get the final velocity in the x direction, and you're going to need to get the final velocity in the y direction. And so, once you get those, how fast it's going horizontally and how fast it's going vertically, guess how you find the total final velocity? If you know, like, its two components. Find the resultant of the two. Okay, and the resultant would be, right here. So we have to go back and find the final velocity in the x and the final velocity in the y. So let's go back over here. Let's make some room.
Don't we already know the final velocity for horizontal?
Yes, we do. Very good. Good job. So we are trying to find the final velocity in the x direction and the final velocity in the y direction. If you have room, you can just keep on going down. If you're going on to the next page, just continue the two columns. Notice, horizontally speaking, if the acceleration is 0, that means that the velocity is not changing. If the acceleration is 0, and originally it was going 10 meters per second, what's that final velocity going to be? We could just write it right on down. 10 meters per second. But in the vertical direction, you're going to have to do a little calculation. Now, you could use the no time formula because you have the initial velocity, you have the acceleration, you have the displacement. I personally like the acceleration formula because I know if I take that acceleration formula, acceleration equals final velocity minus the initial velocity divided by time, change velocity over time. If I rearranged it, you get another common look on that. It's acceleration equals final velocity. No. What am I talking about? That's what we just wrote. Final velocity equals initial velocity plus acceleration times time. That's just this rearranged.
Why isn't that just a legitimate formula?
It is. It is. You can go right to that.
Yeah.
And many people do. And of course, in this case, what was the initial vertical? 0, so that goes there. So the final velocity is just going to be equal to the acceleration, which was negative 10 meters per second squared, times the time, which was 1.73 seconds. So that final velocity in the y direction is equal to 17.3 meters per second. And I'll keep that 3 there because it's not my final answer.
You could also use like the no time formula, right?
Yes, you could also use the no time formula.
Wouldn't it be negative?
It will be negative. Thank you very much, because it's going down. Thank you. And now we go back and do our little vector triangle. We know that right before it lands, it's going positive 10 meters per second, but it's also going downward negative, 17.3 meters per second. Did I have my units right over there? Yeah, meters per second. So that, notice I don't put this triangle in the horizontal or vertical column because now I'm kind of like breaking out of that mold and I'm combining the two motions and I'm finding the resultant velocity. So this is just the total final velocity. This is the final velocity in the x direction, and this is the final velocity in the y direction. So, of course, since it's a right triangle, I can use Pythag. C squared equals a squared plus b squared. C squared equals 10 meters per second squared plus 17.3, 17.3 meters per second squared. And if I solve that, don't forget to take the square root.
20. It's rounded.
Round it. Meters per second. So that's how fast it's going, right before it hits the ground. But since it's a vector quantity, we also have to find the direction. And remember, you always find the direction at the tail of the vector. So right back here. And And when you find that, that's just going to be like a SOHCAHTOA. You could use inverse tangent.
Inverse 10, like negative 17.3 over 10.
Exactly. Tangent equals opposite over adjacent. So tangent theta is going to equal negative 17.3 over 10 meters per second. And what do you get for theta?
60 around.
60?
Around.
So it's 60 degrees below the horizontal. And you could just say that 60 degrees below the horizontal.
300 degrees.
Or you could say at 300 degrees. Or you could say 60 degrees clockwise from the positive x-axis. But you do not want to say 60 degrees south of east because, you know, it's a horizontal. Like, you know, this might be south this way, and no, east that way.
You have no idea what direction.
And that way could be south. You know what I mean? And that way is north. So if this way is east, it's not, you know, it's like 60 degrees down of east.
Is 3D?
It's a what way?
Like, is there anything that we?
Oh, of course. All of this could be done in 3D. So I'm just going to say final velocity equals 20 meters per second at, I'm going to say negative 60 degrees. So the bottom line, people, how can horizontally shot projectile motion problems be solved?
T-chart.
Consider the horizontal motion and the vertical motion separately. Make a T-chart. So you can now do lesson number 2. And tomorrow, we'll take on that big lab.
Are we going to get the calculations?
Are you sure you're raised?